Today we're going to talk about microscopes and tools of their trade. And this is slightly a follow-on of what we were learning yesterday, not only in the practicals, but what Joachim talked about. So something that motivates why we're doing a single particle is applying it to systems like this. So this is a David Goodsell painting of a pancreatic cell. The yellow crystals you see are insulin, vesicles are fusing in green, and then it's going out to the extracellular matrix. And the idea is that for structural biology, we can use these tools to not only understand this process, but understand how the whole mechanism works in real time. And that's a challenge because something that we tend to do is look at things in static snapshots. Now, the tools and the scales of biology needs to fit within a big range from atomic level all the way to quite a bit of size on the micron, if not millimeter level. Aspirationally, we can even get larger. And there are a lot of biophysical tools, structural biological tools that can be used to access different regimes. And something that probably motivates why you're here as well is that electron microscopy can bridge a lot of these modalities together. So I don't want to say that electron microscopy can do everything. The main thing is that you can start doing intermodal, multimodal, and interdisciplinary work by tying together everything using electron microscopy. So what is possible today? When people think of cryo-EM, they primarily think of the modality of single particle analysis, primarily because you can go from images to reconstructions within a matter of hours aspirationally. And we heard about the resolution revolution, and there were a lot of developments. So direct detectors is claimed to be one of the main pillars of that, because on a standard microscope, if you add a direct detector, you go from sub-nanometer to all of a sudden angstrom scales. But along this time, there were a lot of other developments that made it more accessible. One thing is the microscopes got a lot more stable, a lot more easier to use, and computation became reasonable. So back in the day, you might be waiting months or weeks for computational jobs. Now, a lot of those jobs are GPU accelerated and can be done in a matter of hours, if not minutes. So hardware and software coming together can do a lot of things. For example, certain heterogeneous and dynamic systems, you may need to collect a lot of data, and you might only use a small bit of that. And through our algorithms, we can tease out particular conformational states and sort through. So usually people are thinking about, okay, I only need that 5 or 10%. What about that other 80%? If you're after that, you can get the whole story, as it were, from a sample, if not from a cell. And the idea is that if you have a pathway, you can tease out that other 80% if your criteria is not only resolution, and it's more for conformational dynamics, or in this case, this example, ribosome biogenesis. So through microscopy, you can get a gallery of images, but these images, what we want to do is put into the context of the cell and build up our model and have better idea of biology and to create other hypotheses to push the fields forward. So in terms of EM, we tend to have three modalities that we think about. There's single particle, there's cryo-ET, and there's micro-ED. And all these techniques can be done using the same microscope. So this is the tool of our trade, an electron microscope. You saw this yesterday. It was developed in the 1930s. And not until a few decades later were these applications applied to biological samples in a meaningful way. So looking at electrons, why are we using electrons? There are a lot of advantages for electrons. They have a small wavelength and they can be focused. Unfortunately, as you saw, if you have a lot of electron flux, you can damage your sample. And given that our transmission electron microscopes are very similar to inverted microscopes, the thicker your sample, the poorer your penetration depth. So that gets you to catch-22, because if you give more and more energy, you have more and more damage. Though you have better penetration, your resolution limited. And it depends on what you're after. And that's why the scope of the scale biology that I was showing you, that an electron microscope can be used as a microscope and access different resolution regimes. But then that Nyquist level of that camera or that microscope may not be the true resolution of the sample after imaging. So there was a thought of how much dose is too much. And back in the day when you're using film or static images, there is a crossover of how much signal to noise, how much energy you're putting in the system, and how much signal you're getting back. And through a lot of work, they showed that there's a lot of visible damage when you get to hundreds of electrons per angstrom squared. But in reality, within the first couple of electrons, you're actually killing high resolution. You're talking about that angstrom level data, your side chain data, et cetera. So there's a balance between how much dose you want to use to be able to process your data, to be able to interrogate particular regions of interest, versus if you're also trying to get resolution. So that's really the balance where people are really trying to push for resolution, but if resolution is your only criteria, that's why in the previous example, you might only be after 5 or 10% of your sample, because if you're dealing with single particles, unless you have a very stable sample, have heterogeneity, not just identity. So it might be identity-wise very homogeneous on a size exclusion or your purification, but conformationally heterogeneous. And so how do you deal with that? Now, the electron microscope, as we alluded to, is very similar to an inverted light microscope. And as you see that there's a source, there are a whole bunch of lenses, you put your sample, the beam goes through the sample, and then you image it. And so if you think about a light microscope using visible light, a transmission electron microscope using electrons. So our lenses in TEM are electromagnetic lenses. Their NA is much worse. Some light microscope lenses have high NAs. They can even be over 1 if you have oil immersion lens. But our electromagnetic lenses are, I don't know what the NAs are, but it's like 10 to the minus 2, give or take. So it's really much, much worse. So if you think about the diffraction limited light microscopes, the wavelengths you use are hundreds of nanometers with super resolution techniques. XY, you could be in 300 some nanometers resolution, which is very small compared to the wavelength of light coming in. Z-axis is a little bit worse, maybe somewhere around a micron. But the TEM, in 100, 200, 300 kV, we're dealing with picometer wavelengths, but typically we're analyzing things in the angstrom level. So that goes to show our electromagnetic lenses are not as good as the glass lenses. However, what's fortunate is that most of biology is in the angstrom level, so we can get away with that. So there can be some improvements for electron microscopes, but the electron microscopes we have for the past few decades seem to be a tool that's good enough to really keep us going and going through the near future. I'm going to touch upon 4 main things when we think about an electron microscope. You might have seen some of these components yesterday, and then when you're on the microscope today, you can reinforce that. We have electron sources, we have a vacuum system, we have lenses and detectors. So if you are conscious about these 4 systems, then most likely you can interrogate if your microscope is aligned properly, as well as how to maintain one. And we can get into that if we want to talk about that during the roundtable. But there are several components here. I'll have these slides up there, but the idea is, what does an electron gun do? Well, that's our light source, as it were. It produces electrons. Right below the electron gun, we have an accelerator stack. So that's where we accelerate our electrons to either 100 keV, 200 keV, 300 keV. And I'll mention a little bit more about that in a bit. Our condenser lens is right below, and it controls, you can think of it as the illumination or brightness. The objective lens, we actually have a split lens with an upper and bottom pole piece. So in our objective lens, with the 2 pole pieces, our sample goes in, and our aperture is right below that. So that's a specific lens that we typically use for TEMs. And then our intermediate and projection lenses control the magnification. And if you're doing micro ED, you can pull some of that out and put your back focal plane onto your projecting plane and see diffraction. There's something known as a fluorescence screen. Back in the day, you actually had oculars, as you see in there, binoculars, but now that's a camera now looking at a flu screen. So when electrons hit a scintillated screen, it'll kick out photons. Sometimes people say electrons are green because back in the day, the scintillation was kicking out those green photons. And then on the TEM, we have a TEM detector. So we're going to go over all these 4 components. We'll start off with electron sources. The 3 main electron sources that you may encounter are filaments, crystals, or field emission guns. Normally, we use tungsten, and the reason why we use tungsten as the main material is that it can heat up to a very high temperature. I forgot what I just showed you, maybe 3,800 Kelvin. So that's quite hot. So if you see below, you can see real images of what a tungsten filament, lanthanum hexaboride or cesium hexaboride crystal looks like, and a field emission gun. And so why would you use one versus another? And the reason why I put a light bulb in there, you can think of that exactly as that. If you had tungsten filament, imagine putting your filament in a vacuum chamber, setting some current in, and you get thermionic radiation. So if you look at the FEG in detail, what you would have to see is that there is work to extract electrons, and that's known as the work function. So what is done in usually a tungsten filament is really very similar, like a light bulb. But for a field emission gun, especially a Schottky emission gun, we heat it up a little bit, and that lowers the work function. And not only that, our tungsten field emission gun filament is usually coated with a little bit of zirconium oxide. And so again, by heating that up, you lower the work function and you can better extract electrons. They're used as a little bit biased. Usually in the extractor, there's 3 to 4 kV, and that helps pull the electrons out, and then you immediately hit a gun lens. So your first lens is really right up against where your field emission source is. So what you see in the bottom row again are examples of a tungsten filament. I don't know if this is a cesium or a lanthanum hexaboride crystal in red. In blue and green are both field emission gun tips. You might hear things like SFEG, XFEG, CFEG. So SFEG is a standard Schottky FEG. So this is a thermionically assisted field emission gun in the sense that you heat it up a little bit to lower the work function and you can extract electrons. An XFEG, that's a Thermo Fisher term, that's an extremely high brightness field emission gun. And then there's something known as a CFEG or an ECFEG. It's a low spread cold FEG. And if you think about a tungsten filament and you set whatever that brightness at a level of 1, a lanthanum hexaboride source can be up to 3 times brighter, and SFEG 250 times brighter, etc. So the reason why people like the field emission guns is that not only they're brighter, if you look at the column below, they have a lower energy spread. So then if you're going for a very coherent beam, then you want a field emission gun because that energy spread is lower. So what happens when your energy spread is very large? So what ends up happening is then the speed of electrons that are hitting your projection plane is coming at different speeds. So then what you would have is you would have a range of delocalization of your image, right? So you want a very coherent beam such that you have your elastic scattering and all that contribution that's coming at your image plane is coming from your sample. But if different speeds are hitting the same sample, then you'll have shadow images at different planes, and then you'll lose some resolution. Something else to think about would be lifetime, because tungsten filament is very much like a light bulb. When you need it, it's on, and when you don't need it, you turn it off. Something like an SFEG and XFEG, you keep on all the time, and it's on all the time. It can last for thousands of hours, if not years, if you're very lucky. And it depends on the manufacturing process. So if you note in blue there, that's an example of what an SFEG looks like, and in green, an example of what an XFEG looks like. And so you notice that for an XFEG, the tip, the probe, is much sharper, and that's where the source size is smaller. And with greater quality control, that's how you can have years of lifetime, potentially. There's a good reference if you ever want to calculate how fast an electron is going. You can go to this YouTube link, but they'll go through the math of how fast a 5 keV electron is going. Roughly, it's somewhere on the order of 1/6 to 1/7 the speed of light. But if you think about the common energies that we use, if we are at 100 keV, you're already half the speed of light. If you're at 300 keV, you're over 3/4 of the speed of light. So that's how fast an electron is going through once accelerated in the TEM. Something to note is that if you froze time, the flux of an electron, especially when we're in counting mode, is not that great. There's probably not too much more than 1 electron in the column in any period of time. But when we take exposures, we take it over several milliseconds, if not seconds, and that's where you get the tens or hundreds of electrons per angstrom square flux that we have. But then if we look at an electron microscope again here, we've mentioned different accelerating voltages. And currently, the different accelerating voltages are coupled with price point as well as class of microscope. I always use the analogy of a car. If you get a basic car, sometimes you don't have power steering, sometimes you don't have a leather interior, but if you get a luxury model, all of that's included. And that sort of goes with an electron microscope. If you've ever bought a light microscope, they're very modular. So if you say, I want, let's say you got Nikon or Olympus, et cetera, you want these objectives, you want this stage, you want, do you want monochromators, do you want other different types of electrons or light sources? And so what that ends up being is that many of the microscopes we use for screening tend to be around 80 to 120 keV. There are a few reasons for that as well. There might be a little bit more contrast when you have a lower accelerating voltage, especially if you want to screen some samples. But the upkeep for lower keVs is cheaper. And so therefore, that way you can get a pretty nice screening microscope in cryo using just a tungsten filament or a lab 6. Recently, there have been more and more developments on using field emission guns for 100 keV, because if you ever analyze the signal to noise ratio of different accelerating voltages for very, very thin samples, 100 keV might give you the better signal to noise versus a higher energy. But there's a reason why we've been using higher energies, and partly due to the detectors, we'll get into quite soon. So 200 keV is something that we've been using during the short course, and that's usually reserved for somewhere intermediate. It used to be reserved for what we considered screening microscopes, but more and more it's being used for data collection microscopes because it's in that moderate range where you would have good efficiency, and our detectors work pretty well in that keV range. So normally when you're in a screening microscope, you only care about being sub-nanometer, but once you get to 200 keV, you can get near atomic. And depending on how careful you are and what mode you're running the microscope, you can really use it as a data collection microscope. But for efficiency, a lot of the 200 keV instruments right now are primarily used for advanced screening, so as it were. The 300 keV microscopes have a lot more bells and whistles. For example, the Titan Krios has a third condenser lens. Some systems have a mini condenser lens that allows you to have a better parallel range. And also it has a lot of additional features. For example, in our lenses, they're constant power, so there's less hysteresis. All in all, what that ends up being is that it reduces a lot of aberrations. And so you don't want to necessarily say, if I want to have good imaging, do I want to correct that in hardware or software? You want to do it in both. You don't want to minimize as much in terms of aberrations as you can, because it'll make your life easier in terms of processing and interrogating if you can push resolution. So these typical microscopes can go in sub 3 angstroms quite readily. And even if it's not perfectly aligned, you can still probably get sub 3 angstroms because they're so stable. There have been other microscopes. There are 1 and 3 megavolt microscopes. They tend to be using lab 6 filaments or crystals. And these are more customized and specialized. They are multiple stories. There used to be one in Albany, but I think most of them now are in Japan. And why are these used? They're probably not used for more of your applications. A lot of material scientists use them because let's say you have not soft materials but hard materials, as well as if you're trying to do things like look through cells or tissues. Okay. So that's a little bit about our sources. And now I'm going to shift gears to talk about vacuums. And so everyone has heard that you need a very good vacuum, and if you have a vacuum crash, that delays your session. But why would we need a vacuum? So imagine if you're sending an electron through air. It probably won't go too much further than a centimeter. So that's why we need a vacuum, because all that energy is being absorbed by that material. In addition, your source will burn out. So imagine you have a light bulb and you remove the vacuum, it'll just burn straight out. There's also the idea of insulation and contamination, because we put our samples. So imagine you have a light bulb where you put your sample in and you also put your detector in. And you can think of that sort of like what's happening in TEM. Everything is kept under vacuum. Your detector is under vacuum, your sample is under vacuum, and your electron source is under vacuum. So how do we maintain that vacuum? We have several sets of vacuums. The pre-vacuum pump, like a rotary pump, is a standard pump that we use. Sometimes that's backing an oil diffusion pump, and then we have turbos, and that could be backing an ion getter pump. An ion getter pump is just basically, imagine a box with getter material. You send a few thousand volts to it, and you have any ion, they'll just be slammed against the wall. So if you think about the vacuum ranges we're going to go from atmosphere to basically near Earth space. So where you have your IGP, you have your IGPs in your columns where you have your samples, but you have additional IGPs basically right on top of your field emission gun or your sources. So you can go from pretty low vacuum to high vacuum, and something that if you notice in the microscope, your vacuum is not the same throughout the microscope. There's differential apertures from separating the gun to your main column to your projection system. So the gun where your electron source is, you tend to have the best vacuum around 10 to the minus 9 torr. It can be even higher depending on if you have a cold fig. The specimen is somewhere around 10 to the minus 6 to the minus 7, and then where you have your detector, it's even lower, 10 to the minus 5 or 10 to the minus 6. There also are differences in modern systems. What I'm showing you here is an example of a Titan Krios. To the left is the autoloader system, and to the right is a column. And so there could be other considerations. For example, if you have a very good microscope, you can keep 12 samples in the autoloader for days, if not weeks. So you want to maintain that vacuum. So not only the vacuum in your column, but the autoloader. What ends up happening is that every so often, whether you're on a side entry microscope or an autoloader microscope, you're going to have to recover vacuum. And the IGPs eventually will get saturated. And maybe through a lot of sample exchanges, you'll introduce contamination. And what you would have to do is known as a cryo cycle. You just basically warm everything up and have the turbos pump out, like the IGPs turn off and the turbos pump out the contamination. The question is, how often do you need that? And that depends on how frequently you use the microscope. So on a screening microscope, there can be a situation where you don't necessarily need to cryocycle the column, but the autoloader, because that's where you're doing a lot of sample exchanges. But that doesn't mean that you can use the microscope if you're only cryocycling one part, not the other. Something to make note, here's an example of a microscope split. So if you look over there, basically the metal rods that are holding out, that's actually holding a grid. So imagine that's 3 millimeters. There's a little hole in there. It's about a 1 millimeter hole, give or take. That's actually the optical axis of the electron microscope. The main optical axis of the electron microscope is actually very small. And the main width of the column is the electromagnetic lenses as well as the lead shielding. And then only when you get to the octagon, as you see on the far right, is where you have the sample and the cryo box. And so this is what it looks like in a Krios system. So I mentioned the main width of the microscope is taken up by lenses, and we have basically it's a magnet. So if you have visible light going through a glass lens, it bends. If you have a magnet and you send an electron through, it'll bend. But something to think about, an electron is a particle and it is a wave. So as your electron is going through the column and going through magnets, it's spinning. And you might notice the lenses can help focus, magnify, but they can also rotate. and the lens system in a normal TEM has defined magnifications. You can have continuous mag if you sort of hack the system, but what you notice is your image will start spinning. So you would be wondering, like, why do I have that mag or that mag? If you had an intermediate mag, if you think about it, if you have an electron going through, you'll have a rotation. And so then you would have to calibrate that. So that's why the manufacturers have set mags, and they align that so it looks coherent as you're trying to do multi-scale imaging. We'll get into this more in the practicals, but usually when the TAs were going through that, they were telling you about alignments and how to interrogate if a microscope is properly aligned. Typically, we go top down from the gun to the condenser system to the objective system, and then finally, anything else that we might need, especially if you had other features, for example, like an energy filter. So you align top to bottom, and you always want to be at eucentric height and eucentric focus. There is a particular range that your lenses can reach. So on certain systems that are not constant power, what ends up happening is if you send current through the lens and the temperature changes, then you have different resistivity. So that could cause hysteresis. So though you're sending the same current through the lens, you might have a differing effect. So constant power lenses sort of minimize that hysteresis, and it can be quite stable, like on a 3-condenser system, for example, a Krios. A Glacius that we have is a 2-condenser system, so we have a less range that's parallel, and you might notice more hysteresis. There are other things that we're not exactly going to cover, but notice that sometimes when we refer to lenses, we also have apertures. So below each lens, we have an aperture. So there's a condenser aperture, there's an objective aperture. And though we refer to them interchangeably, just note that usually when we say we're going to put in the objective, we're using a shorthand that we're putting in the objective aperture, not literally the objective lens. During the time here, you're going to be able to, especially after you're done the first practical, you're going to start looking at your samples. And we haven't gone over image formation so much, but that'll come tomorrow. The idea is that there are ways to, on the fly, determine if your lenses are aligned properly, if the microscope is aligned properly. And for example, you can take an FFT of an image, and if you have strong signal, you can see something like what you would want in the panel A. What we call stigmation would be in B, and then you could see something like drift, where you have a high resolution cutoff directionally in C. And if you notice that the image had different rings, those are tone rings. So the TEM has aberrations, and what we can do is there's an equation that can fit those rings and estimate the aberrations coming from the microscope. And we'll get into that more tomorrow, but if you look at that equation and you look where focus is, delta F, you may have a better idea of why we collect under focus. So the CTF looks quite a bit different if you're under focus versus over focus. The Cryo VR team actually, has a very good CTF calculator. I think we'll post that in the Slack channel, and you can start playing with CTF and see what happens when you go so far under focus or over focus. And that will impact when you're doing the processing practical in a day, what happens when you use different box sizes. But a practical application of visually in real space, what happens if you're over focused, you'll see the left panel there. If you're in focus, the middle panel, and then if you're defocused, the right panel. And if this doesn't seem that apparent, when you go to the microscope for the practicals coming up, you can actually ask your operator, say like, okay, what's an over focus, in focus, or defocus image look like? So lenses can do quite a bit. We also use our lenses to deflect the beam. So something known as APHIS, aberration-free image shift, or image beam shift, has been now utilized. So back in the day, for best quality data collection, we did on-axis data collection. So what that meant was you move the goniometer to your region of interest, and then you collect that image, And then when you want to collect another image, you move the goniometer to another region of interest. So that ends up being quite slow. It is the highest data collection or highest quality data collection because you're always on axis and you have the minimal aberrations. But what people do in modern days is that they stage shift to a particular area and they use their lens to image shift and then beam shift back to the detector. And therefore, in one stage shift, you can get a lot of images. You can think about that though. So if you are in a static location and all of a sudden you image shift and then you beam shift back to your detector, that will cause beam tilt and aberrations. And that can now be corrected in not only software, but hardware. So there's a calibration matrix that we can do to minimize not only coma, but stigmation and defocus introduced by that. Because you think about that, if you're on axis, that's a particular path. When you're still starting to image shift, that's a different path. It's actually going to get longer and longer. And then you might notice when you're actually doing data collection, you set a particular, even if you had a static defocus, when you're starting to image shift, especially extended image shift, you'll notice you'll have a distribution within your defocus. That being said, there's also a situation where most grids are not flat. Even if you have a flat grid, it's typically on some angle, anywhere between 1 to up to 7 degrees. So that's also another contribution for that. Right. So now we'll shift to detectors, and we're talking about detectors. There are different types of detectors, CCDs, CMOS detectors. There are the CCDs that we use for, let's say, like the SATA camera for screening, et cetera. And they may have a phosphor plate and coupled with some fiber optics. And what ends up happening is an electron hits that phosphor, kicks out photons, and then it's read by a fiber optic bundled detector. CMOS detectors are direct detectors, or can be direct detectors. Well, how should I say that? All the direct detectors are CMOS detectors, but there can be scintillated fiber optic phosphor CMOS cameras. But there are no direct sensing CCDs right now. And this underscores that you saw this image yesterday, but the idea is that are you directly detecting that electron, or is an electron being sent to a scintillator to kick out photons? Something to think about. If you look at that, direct detectors perform better at higher KeV. And the reason for that, especially if a back-thin detector, is that when the electron hits the detector, you'll have a single event. If the electron is going very slow and it hits the detector, you can have secondary events and shot noise. So that's why if you look at a lot of the modern cameras, the performance at 300 keV is better than 200 and better than 100. And so that's why when we were pushing for lower keV FEG instruments, we don't reach the same resolutions as we could theoretically, primarily because our detectors are not performing. And so there's a lot of development right now on hyperpixel detectors or 100 keV detectors to better utilize that form factor. If you're thinking about detectors, not only in electron microscopy, but light microscopy, there are a couple terms thrown about, MTF and DQE. So you can think of, there's a certain point spread function. If you take the Fourier transform of point spread function, you get the MTF. So therefore, that is a characteristic of the sensor. DQE is basically a measure of signal to noise, and therefore, depending on your signal, your DQE will change. And that's highlighted here, where the DQE of the detector will improve the lower your voltage or accelerating voltage is at. And the reason for that is that if you're trying to analyze different electron hits, if you have lower fluxes and you have lower accelerating voltages, you potentially could have a better DQE. But there's a crossover in the sense that if you do get that shot noise, a higher accelerating voltage would be better. And you can see different curves in journals, you can compare to different cameras. The ideal camera would be across all the frequencies a very high signal to noise ratio. So a US 4000 shown there, that was what Joachim was searching for. That's what a CCD camera would be, and that's the lowest curve on that right. And all the rest are direct detectors, and depending whether you're using them in integrated mode or in counting mode, you have differences of DQE. So what do I mean by that? Integrated mode would be you're using your direct detector very similarly to a CCD. In counting mode, you lower your fluxes such that you can count single electron events. So it's not so apparent how good a CCD versus a DDD or direct detector is. So one thing you can do is you can take an image of both, and then if you take an FFT, you can see where your information limit is. So the further you go, the more information you get. And two of the main cameras that we've been using are a K3 from Gatan and a Falcon 4i from Thermo Fisher. The Gatan detector is a rectangular detector, and it can use super resolution techniques. So what do we mean by that? In counting mode, what we have is your physical pixel is your image pixel. In super resolution, you have you quartile your pixel. So basically you go in each quadrant. And using super resolution light microscopy techniques, if let's say electron hits in the upper left quadrant, and you can see that hit that pixel, and you can see the bloom effect on the neighboring pixel to better centroid that. And so that's why if you take a super resolution image and you bin it back, you actually have a higher DQE versus just the counting or super res, because by doing that, you're better centroiding your electron event. There are other things that are done to increase your DQE. For example, correlated double sampling. So normally when you're taking an image, you want as fast frame rate as possible. Why do we want that? That way we reduce motion in the sense that we can, if we have a very fast frame rate and we have something moving, we can do motion correction to take care of that. So then we tend to use all our frames for imaging. So what we have is we take an image, we reset the pixel, take another image, reset the pixel. But what happens if 0 is not necessarily 0? Let's say your blank is not that good. So what you can do is you can read out initially, and you can then take the exposure and you can read again and you can subtract that. And so therefore you get a better DQE because it's like you're taking a blank. The problem for that is your camera has a particular frame rate. So normally when you're collecting in CDS mode, you have to use half your frames to take that blank, as it were. The Falcon 4 is a little bit different, and when we get into our processing module, you'll see that a little bit more. There's something known as EER formats. And unlike a standard direct detector like a K3, you have to set your frame rate ahead of time, and you have to set whether you're doing counting or super res. Electron event representation is basically a table of XY coordinates with a timestamp. And so what this file format allows is that after your experiment, you can bin those events and create your own frame rate, and afterwards decide if you want counting or super res. Okay, so that's just a different idea of the file format and different way of setting it up. So the EER format allows you to decide all that in processing. You can somewhat do that in normal K3 data, but if you're collecting every 50 milliseconds, then you can only bin it. Either you can have 50 milliseconds, 100 milliseconds, 150 milliseconds. But with the EER format, you can bin however you like, and you can have variable frame rates. So therefore, if you note that you have a sample that has high drift, either you would have to have a shorter frame rate and you can do a running average so you have enough signal to noise, or an EER after the fact, pending you're still in good DQE, then you can decide what your frame rate is. So we use a lot of terms, especially when we get to the processing. We have to be careful, because if you're applying certain terms for one type of manufacturer, one type of experiment, that might not apply to the full field. In practice, our images, as I was talking about, are not static images, but they're movies. So that's where we can have the power of processing, and we can do motion correction to gain back resolution. So even if an image is moving, and this is an exaggerated version of a rotavirus in a long exposure, that the image over time is not static, and even the particles within that image may not be static. And that's where you would do not only whole frame alignment, but per particle alignments. So as you see, in terms of the resolution revolution, the microscopes is a key part, and the detectors is coupled with that. And something that we'll see tomorrow is more on the computational side. But there have been thoughts on how do you push resolution, and something that to prompt you when you go to do the screening practical is to understand when you're going from screening to data collection, there are certain considerations. So the main part of doing screening on a TEM is not only to interrogate your sample in terms of ice thickness and particle distribution, but to determine what your experimental parameters would be for data collection. And therefore, would a phase plate be helpful? Would an energy filter be helpful? Would having the objective aperture be helpful? Would collecting closer or further away from focus be helpful? Or would having a longer dose / exposure be helpful? In this particular example, Raudo was looking at GPCRs and found that don't use phase plates, anything but phase plates. But whether you have an objective aperture in or out doesn't really matter. Collecting closer to the focus versus farther away from the focus might be a little bit better. But if you have something small, an energy filter and longer exposure / more dose might be helpful. However, look at those error bars. They're all sort of within range. So the only thing we can say is just don't use a Volta phase plate. And why is that? By using a phase plate, you basically are removing signal to gain amplitude contrast, or you get phase contrast rather. So particles look really nice, but you're losing information. And this underscores a point when you're screening and you're looking at your images. You could have a very nice looking micrograph, but it could be a very low resolution, nice looking micrograph. So just note for screening, yes, you turn up the focus, yes, you put the objective aperture in, yes, you might have a larger field of view. But again, note that it's for screening, and also think about how that would translate for data collection, because once you start data collection, you don't want that feedback, though you can have on-the-fly processing and you can get that feedback. You don't want to wait and like, oh, okay, I collected on a quarter of my grid. I realized I want these imaging settings. And the other 3/4 of the grid might not be of same quality. So we're talking about single particle primarily because we can get near atomic. I don't know if 1.1 has been reached, but it's like 1.15-ish. So depending on what modality you're in, we all can reach high resolution, and tomography is a field that's up and coming. So if you think about it, a couple decades ago, for a single particle, we were also somewhere around the 3 angstrom range. And that just goes to show that whether you're doing tomography, single particle, whether you're doing 2D electron crystallography or micro-ED, you're using basically the same microscope. And through the years, that has helped us. And something that we've noted is that EM has reached 3 to 4 angstroms quite really several decades ago. But why did it take not until 2012, the direct detectors? But since then, we've been able to not only get static structures at high resolution, but heterogeneous samples at high resolution. And then that's where you can start getting a whole ensemble and a whole pathway. And we can really get close to near atomic. But the problem with just going near atomic is that if resolution is your only criteria, you're going to miss the full story. So the main idea would be, can you use this in conjunction with a lot of other techniques to really understand the full system? So sometimes you might have purified systems, sometimes you have pleomorphic systems. And EM, as I mentioned, can access all these resolution ranges, but you may not be able to use the same sample across all the resolution regimes. So therefore, you might have to prepare the sample multiple times, use different instruments and different techniques to gain the information you would like. Because sometimes you would not only like to know high resolution structures of a particular component, but context and systems level information. But we're going to focus, again, since the scope is single particle, on more the single particle SPA analysis. And you've all done this yesterday, where you've taken something in bulk, you tried to thin it down, primarily probably through blotting, to get a very thin sample, a thin homogeneous sample. Unfortunately, this process means we're throwing a lot of the sample away, and we hope that we have highly imageable grids. And the idea of single particle is not only to get very thin samples, but to get a good angular distribution such that what we want to do would be reconstruct our region or molecule of interest, rather. The hard part when you're putting a sample into a microscope is interrogating what is a good grid. So are these good grids? What happens if I told you both grids gave 2 angstrom resolution reconstructions? What is a good grid? What is a good micrograph? There are ways of having more efficient data collections because you don't want to spend a week doing a data collection. You would rather spend a few hours. But what, again, would a good grid be? And that's something to think about when you're screening, where most people are using real estate as a criteria. But let's say on the grid on the left, you only need 2 grid squares to get a 2 angstrom reconstruction. You probably have enough real estate. For convenience, I would say the left is more challenging for data collection because I can't automate it, and it might be a little bit more manual. I would prefer maybe something on the right, even though half of it's too thick because I have more real estate. But at this mag, I can't even tell, because if you look at all those squares and they're all cracked and fractured, that might not also be convenient. But to underscore that, another part of what we use day in, day out are EM grids. And there are different form factors, primarily because they're coming from room temperature TEM, pathology, even material science. And there are different materials that grids are made out of. We tend to use copper because it's very malleable. It's non-iron containing. And the other form factor we use are gold, because if you want to grow cells on it, it's not cytotoxic as copper is. But there's a few concepts that we want to clarify. A grid is this 3mm metal mesh that we put in the microscope, and there is a mesh. So what is the mesh? A mesh is basically a pitch. So 200, 300, 400 mesh or standard sizes that we use. But what that ends up being is that there's 50%, 40%, 35% transmission. So if you just are randomly going through your grid, you most likely will hit a grid bar. So you tend not to want to just go randomly, and you want to be very directed. Something else to think about would be, what is your mesh size, because that could impact your reproducibility. So a grid is this mesh. What is on that mesh? It's called a foil. And be very careful, because a gold grid is just a gold grid. And you can get a quantifoil gold grid and has carbon on it. So if you say gold foil, gold grid, then you mean that it's all one material. And why that is very important is that your foil and your grid, since they could be the same material or differing materials, will have different thermal contraction rates. And so molybdenum and carbon have very similar thermal contraction. Copper and carbon do not. And so that's where you can get beam-induced motion, because what could happen is that your foil is under strain versus the grid. And when you put energy in the system, then that is released. Typically, you'll see that it's doming into the beam. Right now, for single particle, a lot of people are moving towards gold grids specifically because of that, because the thermal contraction rates. And you can see an example here where, let's see if I play that again. If you image a hole, a carbon hole versus a gold foil hole, there is, especially in cryo conditions, when the beam hits something that's under tension, that can put enough energy in the system that releases that tension. Versus if it's all the same material and it has good conductivity, there's less motion. So does that mean that for single particle you always want to use gold grids? There are compromises because you also have to think about what your system is compatible with. But there is a great movement towards gold grids primarily due to the fact that you can reduce beam-induced motion. And for some samples, that even without a lot of heavy processing, you can really push. Okay, so I'm going to skip a few things just for the sake of time, but you can think about that. So I showed you a particular diagram of, the particular movie was grow yellow in solution, and we try to thin it down. But what we tend to do is on our grid, we go from our tube with low surface area, high volume, to high surface area, low volume on our grid before we freeze it. And so what that ends up doing is it introduces interfaces. And there was a question yesterday about air-water interfaces. So over the course, even if you were able to apply your sample immediately before the 1 millisecond that it can freeze in liquid ethane or liquid propane, there is enough energy that a particular molecule in solution will encounter the air-water interface multiple times. And you might say, like, if you blot away or you protect an interface, then that might help, because it's been shown that when a macromolecule hits an air-water interface, there can be denaturization or interaction such that you have preferred orientation. If you ever took tomograms of your single particles, you will notice that less than 10% of your samples look like the upper right, like alloys. That's perfect, right? You have a monolayer of macromolecule with just a few layers of water on either side. In reality, most samples are interacting with one, if not both, air-water interfaces, and might be interacting with itself and creating other effects. And so partially when we're doing our sorting and data analysis, we're throwing away a lot of particles, again, it's primarily because we don't understand sample preparation that well. And some of the particles we're removing could just be due to processing, because usually when you're focusing, you're looking at one image plane versus another. So if you're looking at even, the second autolysis example, and you're only focusing on one plane, you would automatically be excluding half your particles if you were only using that as a criteria. Most programs now can do per particle defocus refinement, and therefore you can claw back a lot of your signal. So I'm going to wrap up for the hour. There's a lot more information I could go into in terms of sample prep and other sample prep and other tools in terms of where we're going into the future. But I just want to leave enough time that what we can do, especially in the roundtable, we can discuss about not just the tools that we've been using, electron microscopes, but certain things that might be of more of interest to you. So before I get too far ahead of myself, any questions?